Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 3. In Unit 2, we are going to study about polynuclear hydrocarbons. In Lecture 1, we will be studying about naphthalene and its derivatives, Part 1. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project was sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this session. We will start our lecture with structural elucidation of naphthalene. So here we will be studying about how we can deduce the structure of naphthalene, what are the positions of the double bonds, and what are Fry's rule and Clar rule. So all these things we will study in this particular part. Then we will move on to preparation of naphthalene. We will look at various methods of preparing naphthalene from various starting materials. We will also study about Haworth method. We will also study about how the Friedel-Crafts reaction can be used to prepare naphthalene. And then we will move on to study about the reactions of naphthalene. So here we will be studying about the reduction reactions of naphthalene. What are the different reduced products which can be obtained from naphthalene? We will study about halogenation reaction. We will also study about single electron transfer reactions. Then we will study about oxidation reaction. So these are all the various topics that will be covered in this particular session. Welcome to the next session. In this session, we will be talking about naphthalene and its derivatives. Let us have a brief overview about naphthalene. Naphthalene is having a general formula C10H8. So it mainly occurs in coal tar. So this is the major one of the component present in the coal tar. Naphthalene is the simplest example of the condensed or a fused polynuclear hydrocarbon containing basic benzene rings. So these compounds are basically derivatives or benzene rings. When we look at the structure of the naphthalene, the neighboring rings, there are two rings here. In naphthalene, we have two rings. The first one I put it as number 1 and this is the 2. So there are two benzene rings fused together and these are sharing two carbon atoms. So the adjacent rings 1 and 2 are sharing two carbon atoms between them. So this is how naphthalene's structure is represented. And when we look at the reactivity, the electrophilic substitution on naphthalene occurs much more readily than benzene. So since this is having a aromatic ring structure, this undergoes electrophilic substitution, and since there are two rings are there, that means the pi electron density is little bit higher than a benzene ring. So that's the reason here the electrophilic substitution happens very readily, and we will also see what are all the different positions at which the electrophilic substitution will occur. And if you look at the uses of naphthalene, naphthalene is generally used as insecticide or pest repellent. So many of you will be using this at your home to get rid of cockroaches and other small insects. You can use naphthalene balls. Of course, this naphthalene is having some toxicity. There is a airway toxicity generated by naphthalene, and this toxicity is actually specific, or it is towards a particular species. Say for example, some of the species are actually affected by the naphthalene much more than the rest of the species. And it is also related to regional and sex differences. That means sometimes the male insect is affected more than the female insect, and maybe in a particular region these insects are affected much more than the rest of the insects from different regions. So the susceptibility of the insect towards this particular compound, that is naphthalene, varies. So that is what here it is mentioning. So there is some selectivity, and based on this selectivity, naphthalene can be selectively used to kill insects. Let us look at the structural elucidation of naphthalene. So we have seen that the naphthalene is having a general formula C10H8. So that means there are two rings are there. So if you look at the number of carbon atoms, we can start from anywhere. So let me put here 1, 2, 3, 4, then 5, 6, 7, 8, 9 and 10. So there are total 10 carbon atoms are there. Along with that, if we look at the number of hydrogen atom, because here at position number 5 and 10 there is a double bond. So this is a quaternary carbon. So because it's a quaternary carbon, there is no hydrogen here. So rest there are 8 carbons are there. All the 8 carbons are having one hydrogen atom. So that is the reason the molecular formula is C10H8. And how do we know this is the structure? We are going to find out how we can actually exactly say the naphthalene is having this bicyclic ring system. So when we oxidize naphthalene, we end up with phthalic acid. So phthalic acid is having 2 carboxylic acid adjacent, that is ortho position. 2 carboxylic acid groups are present in a benzene. So that compound is called phthalic acid. And again, if we do the nitration followed by oxidation, we end up with a nitrophthalic acid. So that means if we look at or compare between the two different oxidation, one is the direct oxidation of naphthalene, the second one is nitration followed by oxidation. When we look at these two reactions, in one case we get a unsubstituted phthalic acid. In another case, we have a substituted phthalic acid. So that means it clearly tells that there are more than one ring present in this particular compound. And if we do an additional reaction, that means if we first carry out a nitration followed by reduction, that leads to a amino derivative, and this amino derivative on oxidation produces phthalic acid. It is not producing a substituted phthalic acid, but it is producing directly phthalic acid. So that means amino group is present in one of the benzene ring which undergoes oxidation. So let us look at how we can actually represent all these reactions in a simple scheme. And these two reactions, that means nitration and nitration followed by reduction, leads to two different type of phthalic acids. That tells that the compound has actually two benzene rings. That means we will have to see whether they are how they are fused, and when we look at the reactions, we will understand how it actually proceeds. So the first one, this is the tentative structure of naphthalene. So there are two rings present. If we assume that there are two rings present, the nitration leads to mononitro derivative as shown here. So when the mononitro derivative is formed, this mononitro derivative on oxidation leads to nitrophthalic acid. So that means the orange ring is retained and the blue ring is broken. So this is where actually the oxidation takes place, which leads to the dicarboxylic acid, and the nitration happened in one of the ring. So this is one type, which tells that there are actually two rings present here. And if the nitro compound is reduced by hydrogen to give the amino derivative. So when we get the amino derivative, and when this amino naphthalene is oxidized, we end up with simply phthalic acid and we do not get aminophthalic acid. So this again tells that there are actually two rings present in this compound. And why we get two different types of products? If we look at the nitro group is actually a deactivating group that all of you are aware of is. So this is a deactivating group, and when it is a deactivating group, the unsubstituted benzene ring becomes more active than the benzene ring where the nitro group is present. So that is the reason this particular the blue ring undergoes oxidation very readily in the case of nitronaphthalene. But when we have a amino group present in that compound, this is actually a activating groups. When we have a activating group, the oxidation actually cleaves the activated ring very readily. So if we look at the nitration and amino derivatives, in these two cases the nitro deactivates, so that ring is not oxidized, amino group activates that particular benzene ring. So, this particular ring is actually broken. So, that is the reason we end up with the phthalic acid as shown here. This is an unsubstituted phthalic acid which is obtained by the oxidation of amino naphthalene. So, these two reactions clearly tells that there are two rings present, and since we are getting phthalic acid, the two the carboxylic acid groups are in the ortho position. So, here again when we look at the nitrophthalic acid, what we get? So, the two carboxylic acid are in the ortho position. So, these two reactions clearly tell that the two rings are attached in a ortho fashion. So, this is how the fusion of both the rings leads to the naphthalene derivatives. And when we say the molecular formula of naphthalene is C10H8. So, from the double bond equivalents we can identify there are 5 double bonds and 2 rings. So, all those things we can actually deduce, and which you are already familiar with. So, with that we have to now find out how the 5 double bonds are actually placed. So, we have 5 double bonds. So, what are the different ways by which these 5 double bonds can be placed? We have to now look at. When we look at the resonance energy of benzene, we have 36 kilocalories per mole. So, this leads to 2 resonance structures. And when we look at naphthalene, naphthalene is having a much higher resonance energy, that is 61 kilocalories per mole for both the rings. So, when we look at a simple formula, if there are n benzene rings are fused in a linear fashion, that is when we have a polynuclear hydrocarbon where n number of benzene rings are fused in a linear fashion, there are n plus 1 principal resonating structures are possible. So, this is a simple rule. So, according to this rule, in naphthalene we have 2 benzene rings which are fused in a linear fashion. So, that leads to total 3 resonating structures. So, we can write actually 3 resonating structures as shown here, and if we look at all the 3 structures, the first structure is actually a very symmetrical structure. If I draw a straight line from the central bond, so what will happen is like this part and this part are actually like a mirror image part. So, there is a symmetry in this molecule. And if you look at structure 2 or 3, we do not have any symmetry present here. Of course, if you can draw a line like bisecting the molecule in this way. Similarly, if we draw a line which is bisecting the molecule in this way, we do have a symmetry. But there is no symmetry in the center, that means where the ring fusion is present. So, we do not have a symmetry across this particular bond. So, that is the reason these two structures are called unsymmetrical structures. So, if you look at all the 3 structures, we have 5 bonds which are distributed in the 2 benzene rings. And based on the stability, we can say this particular structure which is having a symmetrical structure is contributing more towards the resonance structures compared to the other 2 structures. So, there is a Fry's rule which actually talks about where are all the double bonds present in this particular compound. That means in the naphthalene we have written 3 resonance structures. And how do we know what is the most probable structure for naphthalene? We can refer a Fry's rule. So, according to this Fry's rule, what Professor Fry had found out was the most stable arrangement for a polynuclear compound is the structure that has a resonance contributor which has maximum number of rings, that is having a benzene like Kekulé electron structure. So, if we go back to the previous one, we have 3 resonance structures, and one is a symmetrical one where there is a double bond at the ring junction, and on both the sides we have 2, each ring has 2 double bonds apart from the ring junction. And the other 2 structures whatever we draw, we have one of the end ring is having the double bond structures. So we can also draw the next one, the resonance structure, with the right hand side one having the 3 pi bonds. So these are all the 3 structures. So this is the most symmetrical one. And when we oxidize the naphthalene, if naphthalene is having a most stable structure, then this will not undergo oxidation very readily. So this is the most important thing we have to remember. And if we look at the other resonance structures, so this on oxidation actually leads to a compound which is similar to benzoquinone. So when the benzoquinone is possible only if there is a bond which is present in the ortho position. So this is the orthobenzoquinone, which can be easily formed from the resonance structures of naphthalene. So these are less stable resonance structures, that is why they undergo oxidation very readily, and this clearly tells that the compound, the naphthalene, is having a structure which is very similar to orthobenzoquinone structure. In other words, the 2 rings are fused in the ortho orientation, and this also clearly tells that the formation of the orthobenzoquinone is possible only through a highly reactive benzene ring. And since he got orthobenzoquinone from naphthalene, he said there are a couple of resonance structures which are actually responsible for the formation of this orthobenzoquinone from naphthalene. In other words, we can say this ring undergoes oxidation to give the orthobenzoquinone. So based on the Fry's rule, we can actually deduce where are all the double bonds that are present. So in the first structure, there are 2 benzenoid rings, and this is the most preferred resonance structure because this contributes more to the resonance. So this is what is called the most stable structure, and this double bond we can assume it is present in ring 1, or we can also assume this is present in ring 2. So between these 2 structures we can always say like the double bond may be present with ring 1 or may be present with ring 2. So that means the stability of this particular structure is much more compared to the other structures. So in this particular case, only this particular ring is having the aromatic sextet arrangement, or the 6 pi electrons are present only in one ring, and in this particular case only the second ring is having the 6 pi electrons arrangement. So that means the other ring is not highly stable. So that is the reason this compound undergoes reactions very readily. And if you look at the numbering and the position that is generally used for the naphthalene, generally the bottom next to the ring junction carbon is numbered as the number 1. In some books people start from the bottom part, and in some books you can see the numbering may start from the top part also, but in whichever direction you are starting, it actually goes in the counterclockwise direction. So you start from here, then you go to the right, the next number comes here, then goes up, then goes to the left, then we actually leave this ring junction while numbering. So after we reach the position 4, that means in one of the ring we start from the bottom. So 1, 2, 3, 4, 4 numbers are given, and the 5th number is not given to the ring junction, but we go to the next ring and then we start the numbering continuously here. So 5, 6, 7, 8 are the numbering. So this is how we generally give the numbering for naphthalene derivatives. And in olden books people also use alpha and beta notation. So the alpha notation is the first carbon from the ring junction, whether it is at the top or at the bottom, both are called as the alpha position, and the next carbon is called the beta carbon or the beta position. Similarly, when we go to the left hand side, we also follow the same convention. So the alpha and beta are basically a old notation which is being used. In some of the books also you will see this type of notations now also. So we also need to know about another rule which talks about aromaticity in polynuclear hydrocarbons, which is a Clar rule. So according to the Clar rule, what we say is there are aromatic pi sextet, that means 6 pi electrons are actually present in any one of the ring, and this ring is connected with other rings without having 6 pi electrons. So in other words, what we can say is, if we have a naphthalene, only one of the ring can have 6 pi electrons, the other ring only has 4 pi electrons. So total 10 pi electrons are present in the naphthalene system. So when we write the naphthalene structures, one of the ring is having 6 pi electrons, and this is what is called the aromatic character for this particular naphthalene system, and this particular ring is actually considered to be a stable ring. So this does not undergo reaction that readily, but the other ring undergoes reaction very readily because this is not a aromatic ring. So in other words, from the Clar rule, we can actually identify which ring will undergo reaction very readily. In the polynuclear hydrocarbons, we can actually find out. So the Clar rule actually tells that the resonance structure of the polyaromatic hydrocarbon that has the largest number of disjoint aromatic pi sextet, that this disjoint is the most important thing when we talk about Clar rule. So that means the 6 pi electrons has to be separated from other systems. We will see some other systems where we have more than one aromatic ring which can have 6 pi electrons. So from that structure we can identify how to draw the Clar structures for the compound. So here we will simply look at the basic understanding what is a Clar rule. So according to the Clar rule, we have to find out which benzene ring, because all the polyaromatic hydrocarbons are having benzene rings only. One of the or the multiple benzene rings which are having 6 electrons within themselves are called the Clar structure rings. And the next ring, when we talk about if we have to draw the Clar structure for other higher polyhydrocarbons, polyaromatic hydrocarbons, then each 6 pi electron ring has to be separated by one ring which is not having 6 pi electrons. So in this particular case, we have only 4 pi electrons in this ring. So the next ring can come here with the 6 pi electrons. So these are called the Clar structures. So if we take a bigger structure, we can easily understand what is the difference between a Fry structures and a Clar structure. So according to the Fry structures, every ring has to have 6 pi electrons. So every aromatic ring can have a 6 pi electron. So these structures where all these 1, 2, 3, 4, 5, these 5 rings having 6 pi electrons. Now the question will arise, because in this particular ring, if you look at these 2 are the pi bonds associated with this particular ring, but the neighboring ring, if you look at the number 2, there is only one pi bond, because if this pi bond is basically common to 2 rings, and if you look at this pi bond, this is again common to 2 rings, this is common to 2 rings, and this is common to 2 rings. So there are multiple places where 2 pi electrons are common to 2 rings, but when we talk about Fry structures, we consider all these things as aromatic system. That means 6 pi electrons are actually present here, and we draw the structures as shown here. So this is a Fry structures. The compound is basically dibenzo BCKL chlorinine molecule. So in the Fry structures, we have 5 Fry structures, whereas we can draw multiple, that means 5 benzene rings having aromatics pi electrons. So 6 pi electrons we are assuming. So that is what is called the Fry structures. Whereas when we talk about the Clar structures, we are only considering the electrons, the pi electrons associated with that particular ring only, and we are not considering the adjoint or the group which are connected to 2 rings. We are not considering. We are only taking that pi electron for any one of the ring. we are not taking that for both the rings. So, in the Clar structure, we have one aromatic ring where we have 6 pi electrons, then another benzene ring having 6 pi electrons, another benzene ring 6 pi electrons. So, like that we have only 3 benzene rings having 6 pi electrons. These are disjoint, that means these are not connected to the next one. So, this structure is called the Clar structure for that particular polyaromatic hydrocarbon. So, when we have to draw the polyaromatic hydrocarbons structures, we can follow two types of rule. One is the Frey structure rule, another one is a Clar structure rule. So, while we are representing, the Frey structure generally gives more number of aromatic pi electron systems with 6 pi electrons, whereas the Clar structure generally gives less number of aromatic rings which have 6 pi electron in it, because whenever we have to mention a Clar structure, there should be at least one ring which separates this two 6 pi electron rings. So, that means here if you look at this is the number 1, this if a number 1A if I put, then this is 2A. So, the 2A disjoint, the 1A actually is separating 1 and 2. So, that is the reason in the Clar structure what you will have is the 6 pi electrons are separated by some rings which are not having 6 pi electrons. So, that is the Clar structure. So, why do we need to know about the Frey structure and the Clar structure? When we talk about the reactivity, this is very essential to understand what is a Clar structure and what is a Frey structure, because the stability is gained by 6 pi electron ring systems. So, that means if I am going to talk about the reactivity of this particular compound, which ring will undergo reaction can be easily explained based on the Clar structure. So, the rings which are having 1, 2 and 3 are having 6 pi electrons. So, they are actually very stable benzene rings. So, they generally do not undergo reaction, whereas the other rings which are not having 6 pi electrons readily undergo reaction. So, to explain where the reaction actually take place, we can make use of the Clar structure and the Frey structure also. Even if we look at the Frey structure, we can actually say this particular two bonds are not present in the 6 pi electron system. In other words, this particular bond will undergo reaction very readily. And if you look at the Clar structure also clearly tells that this pi bond is not having 6 pi electrons in its structure. So, that is the reason this particular bond can undergo reaction very readily. So, this is how, by knowing what is the Clar structure or what is the Frey structure, we can very well explain the reactivity of polyaromatic hydrocarbons. Let us move on to the preparation of naphthalene. So, we will start with the simple method. The first method is the passing 4-phenyl-but-1-ene over a red hot calcium oxide gives naphthalene. So, this is a simple cyclization reaction which leads by the loss of 2 hydrogen molecules. We end up with a cyclized product from the monocyclic ring. There is also another process in this one, it is a two-step process. Here 4-phenyl-but-3 enoic acid. So, we have the enoic acid and this undergoes dehydration to give 1 naphthol, and this 1 naphthol on treatment with the zinc dust gives naphthalene derivative. So, in a two-step process, 4-phenyl-but-3 enoic acid on dehydration gives the corresponding keto derivative. So, this keto derivative undergoes tautomerization to give the corresponding enol derivative, and this enol has the hydroxy unit. That means, this is nothing but the naphthol, 1 naphthol, and this 1 naphthol on treatment or heating with the zinc dust leads to dehydroxylation. removal of this hydroxy unit, that leads to the formation of the naphthalene derivative. So, this is one of the method by which we can actually make naphthalene. The next one is the preparation of naphthalene. It is a multi-step reaction. Here orthosilylene dibromide. So, this compound is having two bromo groups attached to in the ortho position. So, this compound is orthosilylene dibromide. This when treated with the sodium disodium methane, this compound when treated with disodium ethane tetracarboxylic acid ester leads to the condensation reaction. Basically what happens is the bromine and the sodium form sodium bromide. So, two molecules of sodium bromide is formed in this reaction, and this removal leads to the condensation or formation of bond between this methylene group and this carbon. Similarly, this methylene group and this carbon, that leads to the cyclized product as shown here, and this compound on acid based hydrolysis leads to the dicarboxylic acid, and this dicarboxylic acid on treatment with the silver salt leads to the corresponding naphthalene derivative, and this also undergoes aromatization. The next method is a Haworth method. So, in this method it is also a pretty lengthy process. So, here the starting point is benzene. The benzene reacts with succinic anhydride as shown here. So, this is nothing but a Friedel-Crafts reaction. So, succinic anhydride when treated with the benzene in the presence of AlCl3 leads to a keto acid as shown here. So, the ring opening actually takes place and the acylation takes place on this particular carbon, which leads to the formation of a keto acid, and this keto acid on zinc amalgam reduction in the presence of HCl loses this particular keto group. So, we end up with a simple carboxylic acid, and this carboxylic acid is actually suitably positioned to undergo cyclization. So, this carboxylic acid on treatment with the sulfuric acid, the cyclization actually takes place leading to alpha tetralone, and similar to the previous step of zinc amalgam and HCl, the removal of keto group, this particular ketone is also removed by the same reaction. So, we end up with the tetralin tetralin compound, and this tetralin compound on treatment with selenium undergoes dehydrogenation, and this dehydrogenation finally leads to the formation of naphthalene. So, this is another method by which a benzene can be converted to naphthalene. So, this clearly tells that there is one ring which comes from the benzene moiety, and there is a second ring which is formed from the succinic acid moiety. So, these two clearly tells that naphthalene is having two ring structures. This is also that means the structural elucidation can also be confirmed by this Haworth method of preparing naphthalene from benzene. Although Haworth method is a good method for the preparation, many times the cyclization of this carboxylic acid is not highly effective, or the yields of these reactions are very poor. So, people also follow a different type of approach, maybe one approach in which the carboxylic acid, that is the after the reduction of the keto group, we have the carboxylic acid. So, this carboxylic acid now has to undergo cyclization to the aromatic ring. So, here instead of using carboxylic acid directly, the carboxylic acid can be converted to the corresponding acid chloride by treatment with ethynyl chloride. So, this leads to the formation of the acid chloride, and this acid chloride can be easily cyclized using AlCl3. So, this is another method, because as you are aware, this reaction is basically the Friedel-Crafts acylation reaction. So, it is a intramolecular Friedel-Crafts acylation reaction. That means the acid chloride and the aromatic system are present in the same molecule. So, in general Friedel-Crafts acylation reactions, we have a benzene and we treat that with the acetyl chloride separately. That means two molecules react together to give the acylated product. In this particular case, the acid chloride and the aromatic system are present in the same compound. So, this is a intramolecular acylation reaction. This leads to alpha tetralone. So, here again there are a couple of other reagents which are also used to convert the corresponding acid directly to the corresponding keto derivative. Say for example, this intramolecular acylation can also be carried out using sulfuric acid, phosphoric acid or polyphosphoric acid, HF, etc. And if we have to cyclize the acid chloride, we can use AlCl3 or SnCl4 kind of Lewis acid can also be used for this second cyclization reaction of the acid chloride. So, we have two ways by which the cyclization can be effected. So, this is the modification of the Haworth method. By this modification, we generally get better yield of the cyclized tetralone derivative. Let us look at the reactions of naphthalene. So, we are actually going to compare the reactivity of naphthalene with benzene, because benzene is the basic or the simplest aromatic unit, and the naphthalene is simply the next homologue of the benzene in the next ring. That means there is one more additional ring is added to the benzene. So, for simplicity, we can actually compare the reactivity of benzene and naphthalene to understand how naphthalene actually reacts with other substrates. So, in benzene we only have one ring, and all the carbon atoms have the same pi electron density. So, that is represented as 1 here, and they have the same self polarizability at all carbon atoms. So, in other words, when benzene undergoes reaction, there is no selectivity at which position the reaction will occur. The reaction may occur at this position or the reaction may occur at this position. So, it does not make any difference because the reaction occurs at only one position, and all the positions, all the carbon atoms, that is all the 6 carbon atoms are equally susceptible to attack in the simple benzene molecule. But when we talk about naphthalene, naphthalene is actually having 2 rings. So, in other words, we can actually represent the structure as shown here, and here the pi electron density is very same on all the carbon atoms. So, all the 10 carbon atoms have the same pi electron density, but what is different is the self polarizability. So, between carbon number 1 and 2, as I mentioned, we can call this carbon as carbon 1. If we start the numbering from here 1, then this is going to be number 2, this is going to be number 3, this is number 4, this is going to be number 5, 6, 7 and 8. So, this is how we can actually number this compound. So, here between position number 1 and 2, if you look at the self polarizability, the number 1 carbon is more polarizable compared to number 2. So, why do we need to know that? Because the reactivity is decided by this self polarizability and other factors. We will also look at what are the other factors which affect this. So, if you look at the bond adder, although we know there are resonance structures are possible, there are 3 different resonance structures are possible for naphthalene. In other words, each bond may have a different bond order because of the resonance structures. So, if you look at the bond order in this particular system, this 1,2 carbon, let us say we are talking about this as carbon number 1, this as carbon number 2. So, this particular bond is having more double bond character compared to this. Here it is only 1.60, that means instead of 2.0, because if it is a double bond, we have to have the value as 2.0. If it is a single bond, this is going to be 1.0. So, this is neither a single bond nor a double bond. Most of the time this is actually towards a double bond. So, why do we have these kind of different bond order? Simply because of the presence of various resonance structures. So, since there are more number of resonance structures, the bond is actually not a single bond or a double bond. It is in between that the single bond and double bond. But when we look at this particular bond, that is the ring junction to the adjacent carbon, this is having only 1.56. So, that means this is not having the higher double bond character, this is having lower double bond character. And if you look at the ring junction is actually having only 1.52 as the bond order. In other words, as you know, this is the symmetrical structure we are writing for the naphthalene molecule. We also have two unsymmetrical structures. So in both the unsymmetrical structures, this particular bond is not having the double bond character. So that is the reason this ring junction is having the lowest double bond character compared to the other all the other bonds. So that is the reason if you look at this particular bond is having more double bond character. So in other words, we can say this carbon, these two carbons can undergo reactions much faster rate compared to the rest of the molecule. So that is where to understand how they are going to react, we do need to know what is the electron density, what is the polarizability at that particular carbon. And this leads to the double bond character, because based on the number of resonance structures, we can say this particular bond behaves like a double bond 2/3 of the times. So here is the double bond order we know, and from that we can deduce this bond behaves more like a double bond, that is not 100%, but it is close to 66%. That's what we say, 2/3 is something like a 66 or 67%. So this bond between 1 and 2 carbon behaves like a double bond 66% of the time, and this bond, if you look at, only 30% of the time these bond behave like a double bond. So in other words, the reactivity is going to be much higher in this particular region compared to this particular region, or maybe in this one. So because of these differences, what we can infer is there is going to be different activation energy for reaction happening at different carbon atoms. In other words, we can say the energy of activation for attack differs at each position. That is responsible for the varied reactivity or a type of different types of products we get during the reactions with naphthalene molecule. So as we mentioned, the naphthalene is more reactive than benzene. So why benzene is more stable and naphthalene is more reactive? Because if you look at the resonance energy, the benzene's resonance energy is only 36 kilocalories per mole, but for naphthalene the resonance energy is 61 kilocalories per mole. This is the overall resonance energy. So that means higher the resonance energy, the compound is going to be more stable. But what in reality we observe is benzene is much more stable compared to naphthalene for many of the reactions. In other words, naphthalene reacts much better or much faster compared to benzene. So how or what is the reason behind that? If you look at very carefully, naphthalene is having actually two benzene rings. So if we divide the 61 kilocalories per mole by 2, we actually end up with the 30.5 kilocalories of energy per mole per ring. So benzene is having 36 kilocalories per mole resonance energy, which is higher than 30.5 for naphthalene unit. So in other words, what we can say is high resonance energy means it is highly stable or better stability. So when there is a better stability, that leads to lower reactivity. So in other words, benzene is having more stable nature, so it is less reactive. Naphthalene is having less stability comparatively, so this can undergo reaction at a faster rate. So as we can say that when we actually calculate the resonance energy per ring, the value decreases as the number of polynuclear compounds becomes more. In other words, those compounds are going to be more reactive. So the resonance energy per benzene ring decides how much they are going to be reactive. So, any structures with less number of resonance energy is going to be more reactive. So, this is what we also can understand from the Clar and Frey structures. That also tells which ring will undergo reaction. So, there are two things we have to understand. One is which one will undergo reaction fast, say which substrate undergoes, like whether it is benzene or naphthalene. Okay. So, there is one comparison between benzene and naphthalene. We have to find out which one will react faster. Then again, within naphthalene we have two rings. So, between the two rings, which ring will undergo reaction faster? So, that is also we have to see. In other words, which position will undergo reaction faster? So, by knowing the resonance energy and by knowing the Clar structures, it is very easy for us to understand and predict where the reaction will actually proceed. So, let us start with the various reactions of naphthalene. The first one is the reduction reaction. So, when naphthalene is reduced using sodium and ethanol, it actually produces the dihydronaphthalene, that is one of the double bond. We can say either this double bond is reduced or this double bond is reduced. That leads to 1,2 or 1,4 product, and both the products are actually going to be highly unstable. So, that is the reason these compounds are seldom isolated. But if we do the same reduction using a different reagent, that is sodium and isopentanol. So, instead of ethanol, if we use sodium and isopentanol, we end up with the reduction, that is hydrogenation of this double bond takes place, which gives a tetrahydro derivative. So, we end up with 1, 2, 3, 4 tetrahydronaphthalene derivative. Tetrahydronaphthalene is formed. And if you do the reaction in the presence of nickel, that means if you are using the catalytic reduction in the presence of nickel, this tetrahydro derivative further undergoes reduction. That means the other aromatic ring also undergoes complete reduction. So, here we end up with the Decalin derivative, which is a completely alicyclic system, and this is basically decahydronaphthalene. So, this is a alicyclic system. So, from the aromatic system we are completely going to the alicyclic system through reduction reaction. So, these are some of the derivatives which are formed on reduction of the naphthalene. And if we carry out the bromination of the tetralin compound, because the tetralin has one aliphatic ring and one aromatic ring. So, we have two types of rings present in tetralin molecule, and when bromination is carried out in the presence of light, okay, this reaction adds the bromine atom to one of the alicyclic ring. So, the alicyclic ring actually undergoes bromination reaction, and this reaction actually happens using a radical intermediate. So, because we are using H nu, that is the light energy. So, the light energy breaks the bromine molecule into bromine radicals, and that bromine radical adds to the alicyclic ring. So, this is a simple radical reaction. That is the reason the alicyclic ring undergoes the reactions, and we end up with the monobromo or dibromo derivative. And if we dehydrogenate this monobromo or the dibromo derivatives, we end up with two different type of product, because here the dehydrobromination, that means the removal of HBr from this molecule, leads to the dialene, that means one double bond is formed. And if both the bromine atoms are removed from the dibromo derivative, we end up with the naphthalene as the final product. So, these are all the reactions of bromine. And if we use iron in the presence, iron catalyst in the presence of bromine, here this is very similar to the Friedel-Crafts reactions which we have seen earlier. So, in the Friedel-Crafts reaction, what we are going to end up with the bromination occurs on the aromatic ring. So this is nothing but the intermediate involved in this reaction is a bromonium ion intermediate. So depending on the reaction conditions, one of the ring undergoes the reaction. If it is a radical condition, the bromine addition happens on the alicyclic ring, and if it is Friedel-Crafts or the bromonium ion intermediate condition, the aromatic ring is brominated. And here again, if you look at the product that are formed, we have because the numbering starts from here. So if you put it here 1, 2, 3, 4, and this is number 5, and this will be number 6. So 5 or 6, because when we are going to number, we have to give the lowest number. So you are already aware of how to give the lowest number for that. So we have to actually start the numbering from this bottom, so that we end up, or we give the least number to the substituent. So that's the reason here we have the 5 bromo derivative or the 6 bromo derivative. So both these derivatives are formed when bromine reacts with tetralin in the presence of iron. So depending on the reaction conditions, we can actually identify where the reaction actually proceeds. If it is a radical reaction, the alicyclic ring undergoes bromination. If it is a bromonium ion intermediate, the aromatic ring undergoes the bromination reaction. So the next one is the Decalin derivative, which is a completely reduced completely hydrogenated naphthalene derivative. So we have two types of product. One is a cis Decalin, another one is a trans Decalin. So here depending on the catalyst what we are using, we can actually get the different type of products. Say for example, if you use nickel catalyst, we end up with a trans isomer. And if you use the platinum catalyst for the reduction, we actually get the cis isomer. So depending on the catalyst what we use, we end up with the cis or trans Decalin. And why the stability of these two rings are quite different, if you look at basically the rigidity of the ring system that is present in the trans isomer prevents the ring flip from happening. So that means it is actually the locked conformation. So, and this is a more stable one. So this is a highly locked conformation. So this locked conformation prevents the trans Decalin from undergoing ring flip, whereas when we have the cis Decalin, this can easily undergo ring flip. So depending on what is the catalyst used, we actually end up with a different type of product. The reduction of naphthalene gives two different type of products. The next one is a chlorination reaction. So here we are talking about dry chlorine as the reagent. So dry chlorine, when treated, dry chlorine adds to naphthalene to give di and the tetrachloro derivatives. So from the formation of the oxidation of these two products, say for example, if we oxidize this compound, we end up with the phthalic acid as the product. And here also when we oxidize this particular compound, we end up with the phthalic acid as our product. So this clearly tells that the halogen atoms are present in only one ring. So that is what we can infer from the oxidation reaction. So because when we chlorinate this naphthalene ring, there are every possibility that the chlorination can go in one of the ring. The second chlorine can also go into the second ring. So that is always possible. So if that happens, then oxidation will give actually chlorophthalic acid as the derivatives. But chlorine actually activates that particular aromatic ring for EC oxidation. So this leads to the confirmation that both the chlorine atom or 4 chlorine which are introduced to the naphthalene goes into only one ring. We also call this as a homonuclear halogenation reaction. And when we heat this dichloro derivative, we actually get 1-chloro-naphthalene by the loss of HCl, and the tetrachloro derivative actually gives mixture of dichloro compounds. The The next one is a single electron transfer reaction. So here sodium metal reacts with the naphthalene to give a colored solution, that is a colored addition compound is formed by the one electron transfer reaction. So there is only one electron from the sodium's outer orbital is being transferred to naphthalene. Because of this one additional electron, we get a highly colored naphthalene solution, and this compound when reacted with water or carbon dioxide gives the corresponding dihydroxy or the dicarboxylic acid products. Here this is simply a disproportionation reaction. In other words, the two molecules of this one reacts with either water or carbon dioxide, giving one product where both the hydroxyl or the CO2 group are attached to one of the ring, and the other ring leads to the formation of the starting material, that is the naphthalene, as the final product. So in other words, what we can say that this is a nice example of disproportionation reaction or reduction oxidation reaction. So one substrate undergoes oxidation, another substrate undergoes reduction. So the next one is the oxidation of naphthalene. So if we simply oxidize naphthalene with sulfuric acid and mercuric sulfate or vanadium pentoxide and oxygen, that leads to formation of phthalic anhydride. So what we can simply say is the oxidation leads to phthalic acid, which may undergo dehydration to give the phthalic anhydride. And if you are using acidic KMnO4, that leads to formation of phthalic acid, whereas if we use alkaline KMnO4, that is basic KMnO4 is used for the oxidation, we end up with the phthalonic acid. So there are two different products formed depending on whether we use a acidic or basic KMnO4 for this particular oxidation reaction. So next one is oxidation using chromic acid. So if we use chromic acid to oxidize naphthalene, we end up with the 1,4-naphthoquinone. If we use ozone, we end up with the ozonide. The diozonide is formed, which on hydrolysis actually leads to the phthalaaldehyde. That means we end up with the ortho dialdehyde in the ortho position. That is what is called phthalaaldehyde is formed. Let us recap what we have studied so far. We have studied about the structural elucidation of naphthalene. So what is the molecular formula of naphthalene? From that, how do we deduce the structure of naphthalene? So how the two benzene rings are attached, whether it is attached in the linear fashion or not. So all those things we have studied. We have also studied about Frey's rule and the Clar rule. What are the application of Frey's rule and Clar rule for the reactivity of polyaromatic hydrocarbons we have seen. We have also seen about the various preparations of naphthalene. So how naphthalene can be prepared from benzene and other compounds we have seen. The Haworth method is an important method by which how we can make naphthalene, and what are the modifications of the Haworth method also we have seen. We then studied about the various reactions of naphthalene. So what is a reduction reaction? So if naphthalene is reduced, what are the different types of reduced products we are actually getting? Say for example, whether we get the Decalin derivatives or tetralin derivatives or the Decalin derivatives. So all those reactions we have seen. We also have studied about the halogenation of naphthalene. So whether the halogenation occurs in the same ring or in the different ring, that also we have seen. Whether we get the mono or the di or the tetra halogenated products, how we get all those things we have seen. We also have studied about the single electron transfer reactions and how we can get the dihydroxy or the dicarboxylic acid derivatives by the treatment of the sodium naphthalene salt, how we can convert we have seen. We have also studied about the oxidation of naphthalene. So what are the different type of products we obtain when naphthalene is oxidized, that also we have seen. With that we conclude this session. Thank you.